All right, so our last speaker today is Mr. Michael Assante. Mr. Assante is the SANS Institute lead for Industrial Control System and Supervisory Control and Data Acquisition Security. So he's industrial controls, leads the industrial control and SCADA training for the SANS Institute. He's also the Vice President and Chief Security Officer of NERC, the North American Electric Reliability Corporation, winner of Information Security Magazine's Security Leadership Award, awarded the RSA 2005 Conference Outstanding Achievement Award, and Mr. Assante is also a former Naval Intelligence Officer and was honored in 1997 as the Naval Intelligence Officer of the Year.
So unknowingly, I wore my Navy pin with great purpose because I want to award the creativity of the designers of this Army badge to deliver a very powerful message, although arguably maybe aspirational only, to the right audience or target, being a Navy guy. But I do actually own a great debt of gratitude to the Army. When I, as a young Navy intelligence officer, getting to do my first shipboard duty of service, it was during the Haiti operations. And it was actually, I wasn't there for that purpose, but that we were retasked. The battle group was retasked from a fleet exercise to perform this Haiti operation. And the United States Army command elements deployed on the Mount Whitney, and also assault elements on our carrier battle group and infantry elements. And that was a great service to me because being a young officer, I totally took a pass on the getting all the things that happen to somebody who shows up for new shipboard service. I didn't have to go find waterline. I got to pass all those things because thousands of Army folks on these naval platforms left the crew, had plenty of entertainment and plenty of things to capture attention. 5 years later, though, I would go to Fort Irwin and have the honor of spending a little bit of time with the OPFOR, and I was christened with all the things you can imagine that a tanker would have to deal with as a naval officer, so that was a fun experience. I have an important mission. I want to orient you to an important operational environment, one where the cyber world meets the physical world, where whether you're going to conduct a defensive mission or an offensive mission is an important understanding about this space in particular. And also, this is a very unique challenge when it comes to our national defense and even being able to support conducting long-term military operations over time is the defense of critical infrastructure. So with that, I want to talk to you and orient you to the problem set, if you will, of industrial control systems or SCADA systems. First of all, this problem set clearly is not one in which we need to worry about vulnerabilities and closing vulnerabilities because it is more than plentiful. A lot of the technology was designed 10, 15, 20 years ago. It was designed in an environment which had a sole purpose. It wasn't connected and has legacy architectures. We've built upon it. Year after year, we've added automation benefits. We've added different architectures, but mostly things had to be backward compatible. So we've just continued to build on a foundation that didn't have security requirements in its original design. Okay? And a lot of these products were designed not by IT professionals in the early days, but by engineers. And we'll talk about those implications. It really means that we will end up focusing on different things from a defensive perspective and also try to understand realities. Important realities are there plenty of attack surfaces. The issue will be not is there a vulnerability in the technology, but how exploitable is it, or what are the pathways to achieve, to get close enough to the attack surface that you have developed a capability against or that you must defend against, or those pathways, more importantly, not to the technology itself, but to the process and effects. And so that's what I want to talk to you here about. Control systems come in lots of different flavors. The simple automation in this building, although growing more and more complex day by day, arguably this morning I heard a lot of people complaining it was a little cold in here, so maybe the automation wasn't doing its job, but the environmental system in this building is automation systems. It's based on control system theory, and it's implemented in various technologies. We also have control systems in large power systems, right? You think when we say SCADA, we typically mean control systems implemented over geographic diversity. In the case of power systems, you'll have measurement and instrumentation in the field and substations, and then you'll roll that information back to a control center. You'll conduct contingency analysis on the state, and you'll constantly war game if we lose a pathway. What does that mean? Can the system readjust within 20 minutes to a reliable state? And you'll work that. You'll control the system for the purposes of maintenance or work, or to deal with contingencies such as storms or assaults against the power system to maintain it. That's a SCADA EMS system. There are what we call distributed control systems, or DCS, that you'll find in an oil refinery. Those systems are very complex. Their jobs are to integrate with machine controls and to regulate or moderate a process, a continuous flow process usually. And you have technology that we have control systems called safety systems. Those systems originally were designed to be actually functionally, not only functionally separated, but physically separated from the control system to provide critical safety features to some of these complex processes so that when we did run into a problem, it could act autonomously to shut that down in a safe, what we call safe shutdown. But technology convergence and change drives lots of different things to include business trends. And one such trend is now we have a creature called an ICSS, which is an integrated control and safety system. I'm very disturbed by that because if you've looked at this problem from many different angles, the safety system was always an issue for an attacker because to achieve an effect, that safety system and its configuration and your inability to get to it through the same path that you can get to the control system was very troublesome to you. It required a lot more planning or more intelligence or another way to exploit or get into the target area. Well, in an integrated control and safety system, that's no longer the case. It's going to share and leverage networking resources, but only have functional separation, meaning the mission of the technology is to do safe shutdown, but it's accessible just like the control system, so it's sharing an environment. So important to think about. Why I believe that vulnerabilities are just the tip of the iceberg. Well, we've actually been quite protected and insulated, if you will, as an industry from the normal vulnerability discovery process. Why is that? Industrial control systems are expensive. A medium-sized plant will have a $5 million control system typically implemented in it. In order to get a fully integrated DCS, for example, a researcher getting access to that is unheard of. So what have we had? We've had security researchers pecking around the edges when they can get accessible firmware for free on the internet from a controller saying, here's a great new controller, and here's the firmware, and here's some practice firmware if you want to check out our technology. And then we've had some inspection on that where researchers have looked at that firmware and said, oh my goodness, you did this wrong, you did that wrong. But very rarely have security researchers ever got to have free access on a very large integrated control system. Therefore, what we've seen is, yes, we've seen a vulnerability reporting explosion in the public world, but it's the tip of the iceberg. I guarantee there's a lot more vulnerabilities in the architectures of a lot of these systems and applications. And of course, we have ongoing problem that we use common technology. Although it's interesting, somebody had said, you know, I've been a chief security officer for a global enterprise, and we had an enterprise environment, and it was highly dynamic, and things would change, and I had my control systems, and you know, I'd say, well, you know, I'm in charge of the protection of the systems that, you know, were implemented 10 years ago. I'd sit down with our power control engineers and had some very disturbing conversations. I said, well, let's talk about the architecture. I'd like to work with you to re-architecture this into a more secure architecture. It'll give you better reliability. Why don't we do that? And they said, well, I don't see the need to do that. Nobody could really attack us in a way that's meaningful. And I said, well, why do you believe that? I said, well, because we don't even know how the whole system operates. It does not instill confidence. I said, the CEO probably doesn't want to hear that. But realistically speaking, they are complex systems. But this vulnerability trend and problem, we can't just chase it. So hardening efforts, right? Yes, that's good housekeeping and hygiene, and we need to do those things. We have to do them in a prioritized manner because there's going to be plenty of those. Here's where we are from a defensive reality if you look at the asset base out there and across different critical infrastructures. And I would argue not all of them are equal. Not all of them have taken security as a fundamental requirement now to operate their technology. So some are going to be behind others. But in a generalization, you could say if the IT world is on generation 4 defensive kind of strategy, industrial control systems are clearly stuck solidly as a generation 2 defensive strategy and platforms out there. We deploy control systems today with limited antivirus protection. And everyone says we've got a partner, it's McAfee or so-and-so. And the truth is, because control systems have highly dynamic file structures and folder structures because they change, a lot of the system is off limits to the signature-based. And we know signature-based security solutions are failing. So we have some very limited protections in place. And quite honestly, one of our number one challenges is visibility. Now, we have some visibility, and we have implemented firewalls, we've implemented intrusion detection sensors on enforcement zones in some industries on the outside, right, where the business network connects into the control system or the operational network, but visibility within the control system network itself from a security perspective is very rare, very, very rare. We don't even have the tools, if you will, to conduct a competent response in forensics in this environment either. We have to customize engineering diagnostic tools like Profitrace or things that will allow us to see field bus traffic and analyze that, but we don't have ready-made. We cannot just take forensic tools right off the shelf from that IT enterprise and move them into these environments very easily. So the defenders are seriously constrained. And the competencies out there for this are very far and few and in between. So we have this important mission from a national perspective. One is to balance all these things, and the question is, these are systems that support engineered solutions. So we might actually have to think cyber in a much bigger context. And certainly that's true of being able to conduct military operations in these environments. One of our earlier speakers had suggested that it's really hard to achieve effects. And I would argue that that is potentially true if you take a pure IT approach to an industrial control system. Now, when you say hard to, I like to say, well, what do you mean? Give me some context. Because arguably, if you don't understand the process that the control system is managing or monitoring or controlling, you could still accidentally cause lots of problems, not only in hijacking processes or slowing down communications within the system, but just not knowing, flipping bits in an industrial protocol is not a good thing when you do it in scale, okay, number one. Number two, so if you're going after high confidence effects, meaning I want to be 95% sure that when I fire this, I'm going to get this result, that becomes more difficult. But that difficulty, that gap is starting to decrease, and I'll explain that here in a little bit. If you look at exploit tools, and these are just publicly released control system-focused exploitation tools or frameworks, that is also growing. What's always very interesting is post-Stuxnet, you see these big, everybody thinks, well, this is really important space, and I need to contribute to this challenge, and you see a lot of tools released just after the June 2010 disclosures of Stuxnet and understanding and analysis. So lots of people focused attention there for a while. And you see these exploit tools publicly available. The challenge from a defensive perspective, and I think Dimitri said it, that he has this graph, he's got the two lines, which is the things that we do, the things that the attackers are doing, and those lines never meet. We're going to have that problem here in the control system world. It's very frustrating that many of our national programs or efforts are assisting industry in just playing a catch-up game to IT enterprise networks. Well, you should have IDS. Well, IDS isn't serving necessarily the purpose completely in this other context where we've lost, and that was we're talking about looking at a world that's 8 years behind in some context, right? So playing catch-up isn't an effective strategy. We have these two dynamics. Number one, the ICS-capable threat pool is increasing. It's growing. Some nation states have built programs. They've identified industrial control systems as an important area set that they want to develop competency in. They are approaching the problem differently depending who they are, but they are certainly growing. We're starting to see observables of that, and I'll go into a little bit of detail about some of those observables. But also IT attacks that can impact ICS just because of technology trends and how we're using common off-the-shelf technology in industrial control systems means that pool gets larger every day anyway. So you have these two dynamics that you're constantly working against. Before, arguably in this world, the ICS-capable threat actor pool, most of the ICS SCADA incidents were non-targeted and non-directed. So I just did a big timeline at SANS. Ed's my inspiration. He used to use great posters to teach the world how to pen test. And so we built a poster in the control system domain. And this year's poster, we timelined out all the significant incidents that have occurred in the world of industrial control systems. And it was very easy to see this shift, where in the early 2000s, and all through the 2000s, you had incidents, but most of the incidents were not targeted directed. Malicious software found its way in a control system network. Definitely bad things happen, but it was never designed to operate in that environment. It was carried in poor architectures or bad practices. Well, come 2010, we're seeing a series now, a change of directed, structured, focused attacks where people are bringing custom tools and they're bringing some level of process and understanding to the problem, and that's going to change the game for us in the defensive perspective. Another kind of interesting dynamic in the adversary space is that you've got opportunities, real opportunities for development. Now, they've always been there for organized crime, but now you've got opportunities like in the Middle East and Asia and Europe, you have protracted conflicts. Protracted conflicts where people have been charged with causing an effect or being able to accomplish some objective over time, and they're learning from it. They're learning what matters, they're experimenting, and in those cases, you have real capability development. And that's so much so, includes campaigns that are moving towards destructive payloads where they're actually trying to destroy data. In the case of, in the Korean Peninsula and also in the case in the Middle East, you had several noted incidents that were affecting infrastructure where the payload itself was designed to destroy data through master boot record overwrites, but If that adversary was able to get that into an operational production network, we probably would have had an operational impact to those business operations, although arguably, RasGas and the Saudi Aramco incident would indicate that there were definitely were business interruptions. The question was, there was no production interruption. Quick ICS attack trends. So these are very concerning because these really have come about over the last 3 years. We have seen ICS-specific targeting. This is where adversaries have actually used ICS supply chains in order to actually deliver malware payloads, in this case Havocs, which CrowdStrike, Dimitri was here, they did some great analysis on what they call energetic bear. They believe they're Russian actors, and those actors have developed a remote access Trojan kit. Only in the last couple of months we found a module that they included which was called an OPC module. I used to joke OPC stands for Oh Please Communicate, but OPC was designed to integrate two control systems so they could talk to each other, or designed to integrate a control system to a business system so it could get production information out of an environment. Well, what's interesting about that is OPC is a clear indicator that there's a control system somewhere. And so this module designed to discover, is there any OPC servers out there? And the OPC server is trying to integrate communications, so it friendly says, yes, here I am. And then you can say, well, what are you and what are you controlling, all the way down to the tag level, meaning what information are you as a server supposed to grab out of this industrial process and pass on to another one or to the business network? What are those values, these tag values? Voltage, for example, or pressure or temperature, right? What's interesting about that, not only is to tell you, yes, I've landed in a place where there's an industrial control system, but it might give you a good idea what kind of process is behind that OPC server. Is it a chemical continuous flow process? Is it a power regulation type of process? Focus on river crossing or gap jumping. The one benefit control systems have had in traditional architectures has been one step away from the business enterprise. At least one firewall. Not so true in the natural gas environment, very flat networks. I remember when I was working in a company, we purchased our first natural gas pipeline in a storage facility. I was all excited as a young vice president because they came to me and said, hey, we're going to do a merger and acquisition. We want you on the team. I thought, wow, security's really somewhere now because I'm on the merger team. That's awesome. Well, the next day I get a phone call from my operations group. I go, I think we have a problem because all of a sudden this whole new network, the IP addresses showed up and we scanned it in the morning. I said, you did? And they said, yeah, we did. And then all of a sudden I got another phone call from the gas VP operations saying the whole pipeline's knocked over. We can't see our SCADA system anymore. I went, oh, that was us. So apparently I should have been invited to the merger talks another week before that, and we wouldn't have scanned the pipeline and knocked it over. Protocol custom capable attacks, meaning the attacker came to the table understanding what industrial protocol they would likely encounter, and they developed a capability or tool set for that protocol. And so we have seen that in a series of HoneyNet research. Trend Micro, Kyle did a great research where he basically mocked up a municipal water system and threw 7 or 8 of those around the world. And then Kaspersky did the same thing. Kaspersky might have been a little more self-serving in it, but I think that, they did this research, and in answering and providing information, what was very interesting was not only were there APT-type actors involved in different things, and they were able to compromise the web-based remote access, which is very common in the water industry as an architecture. But once they got there, some of them used protocol-capable attacks. That was eye-opening. They were ready. When they found it, they were excited. They used their tool. They used the right tool. Several of them actually conducted attacks where they actually went after effects. So they scheduled pumps turning on and off in the HMI at the application layer. In some cases, they injected into the protocol to actually send a command set down to the field control units. And in other cases, they actually messed with the firmware. ICS-specific exploit tool, yep, researchers are doing that. ICS-specific exploit tools in use. HoneyNet pot research, we saw that. Process-focused effects. We've had real-world incidents that actually have had process-based effect outcomes. So they actually shut machinery down or open valves that shouldn't have been opened and cause emergency shutdowns and those types of events now. We've seen this in several incidents. And then firmware. Firmware is the system software on embedded devices like controllers. This is an area that arguably you could do a whole lot at the application server level. But when you get down into the field elements and instruments and the controllers, that's firmware-based area. And quite honestly, if we have we have some understanding and capabilities in the network application level, but you get down to embedded systems and our security capabilities start to go kind of down the drain. And unfortunately, firmware is very important as it relates to effects. The controller is where the rubber meets the road for an action in the cyber to physical world. So seeing adversaries go after firmware have been very disturbing. In many cases, they just pulled the firmware off the device And in one case, Kaspersky reports that they modified it and put it back. And that could be a big problem. And then finally, data destruction, that's an issue. So discoveries do happen. We've typically have not seen a lot of incident reported because there's not a lot of capability to detect them. Lots of times when you go out in the field, it's very common for a process control engineer to walk up to a PLC and it hasn't been behaving right. So zero eyes, shut it off, turn it on, power it off, power it on. Might do it 9 times. Eventually it'll work and be stable. We've probably lost lots of opportunities to identify real-world incidents that have had effect all the way down to the field controller level because of some of that culture, if you will. But you can see here, this is disturbing because in this incident, this is in a mining company. They've absolutely suggested the attackers knew what they were doing and actually disabled auto shutdown protections on equipment to cause destruction of the equipment. And the mining industry has all of a sudden, lo and behold, in the last 2 years, people don't think of high technology from a control system perspective, but they've been receiving lots of attacks specific in the Pacific area. Most of them are HMI-based. Attack pathways to control systems, there's lots of them. There's the interconnected network level at the top there between external networks, typically third-party suppliers. They're vendors for the control system. And then the business networks themselves into a plant production floor environment is a very clear path. Some people are implementing data diodes, one-way connections, in order to try to control that attack surface. A lot of industries aren't. It's a very expensive way to do business and very limiting in what you can do then and interact with that production environment. Your support environment is when technicians come, they either bring field laptops or they bring USB sticks with the latest firmware and they show up and this is how they do business. And it's very common. This has been the vector of most of the non-target attacks have been malware accidentally carried in from a technician's laptop the night before in the hotel or whatever, and then he walks in, plugs in, and gives you an infection. It's also reportedly through, if you read public reporting on Stuxnet, the theory that somebody brought an infected USB stick into the facility that ultimately was the target. Field devices, safety systems, down the instrument level, you have to worry about supply chain, where they come from. Most large integrated control systems will be developed, have significant feature development in India, integrated with hardware or married in China, and then some factory acceptance testing. They pull it together in different locations closer to their customer markets, typically, and then implemented it in the infrastructure. And then finally, calibration. This is an area that nobody protects. So when I'm out in the field and I'm working at a refinery or a power generation unit, you say, okay, show me all your calibration equipment and how you control access from the calibration equipment to the safety system. And they'll go, what are you talking about? We have to calibrate those things. And they go, why would you care? Because most modern calibration instruments like fluke meters are just computers. They're designed to plug in right to your laptop so you can download features or you can download firmware for the calibration device itself or pull data off. It's absolutely a very effective attack path to a control system is calibration equipment. Everyone calibrates instruments. Do you have to do it? Everyone go down and touch things. They'll touch controllers to pull data off using calibration equipment. And it's that funny little yellow device that nobody will recognize as a computer. So that's a very dangerous pathway. And so this is we have a very large attack surface, if you will, when it comes down. Dimitri, everyone mentioned the difficulty of asset management, right? Knowing where you've got things. Well, believe it or not, back to my comment, no one knows how that SCADA system worked. Again, we have really significant inventory issues on a lot of different infrastructure, and the control systems aren't seamless. So in a pipeline alone, you will have a SCADA system for the pipeline, but you'll also have PLC-based skids at the compressor stations that manage the compressor operation to put pressure on that pipe, but totally separate and usually owned by different people. And so there's a lot of gaps and seams in an industrial environment when it comes to this technology. And I know the U.S. Army is struggling with it just in the facilities around our bases. We're worrying about how much control systems do we have, where are they, who owns them, and how do we make sure that they're within our purview. These are difficult things. I used some Army stuff up for you guys. I figured that was appropriate. I took all the Navy analogies out. But if you think about exploiting these surfaces, you know, you've got the traditional beach assault, which is I'm going in the front door with everything I got, and I'm going to see if I can get on the business network. You've got spear phishing, which has been used by certain actor groups very effectively for infrastructure, in particular energy and nuclear, and water holing as well with Havocs. We're seeing that right now, basically compromising ICS suppliers and PLC manufacturers with the malicious software. You bring down their software, you bring down something else. So that's kind of raid sniping into typically an operational support network. It's usually a segment of the business network, or it can actually be a segment off of the control system network in many cases. And then finally, the big thing is if you do that, it's about the river crossing. I've got to get from this operational support network onto the control system network. That's my next challenge that I have to defeat. Or you can go for the airborne assault move, which is right into the control network You could do that via that maintenance laptop, by a calibration device, by a USB stick, by even going to the internet. Engineers are great folks because they just want to make things work and they want to make life better for people, but they'll share project files on the internet. And you see all these discussion groups out there where an engineer says, hey, I'm a Pakistani water engineer, I'm working on this, and I can't figure this out, or I did figure this out and I got a great project, does anyone else want it? And people will download these files and implement them in controllers. So if you want an airborne assault, just go follow the engineering forums. So here's an interesting part of a control system. From a defense perspective, the only area we typically focus on is the cybersecurity signatures. Those are enforcement zones or AV files or host-based protection on some servers. But the truth of the matter is, if we're going to conduct comprehensive or holistic defense, we need to work across the spectrum of elements associated. Everything from the physical people data, how project files and data moves to the control system, to the ICS network itself, the control system's behavior. This is an area where they're under-instrumented. They instrument the process, but they don't instrument the actual ICS to say, why is it so slow? Why are we having problems over here? These are areas we need to move into. The process behavior. Not many folks could tell you what attacks would look like against a certain process. What should we look for? Not a lot of work has been done there, and that's unfortunate. It's an area that obviously attackers, when we do our work, that's where we live. In targeting, we try to understand what can we make go wrong in this process, and what will the artifacts be, and how do I deal with those? If that's your operating environment, you're going to get good at process behavior. And it takes the work. It takes combining engineers. And then finally, you hope to cause a physical outcome for some attackers, or some operations call for that physical effect. Some might be limited duration. Some might be a total kill. I want to destroy a turbine generator set. I'm going to do it, and it's going to put them down for 12 to 15 months. Okay, that physical effect or outcome. Now, what's disturbing is to effectively defend these systems, it requires an integrated set, a team. It's not only cybersecurity professionals, but it is bringing in engineers who understand the process and the industry application, if you will. Well, for us to be successful operating in the environment, we need those elements to come together in a way where they can work together. They develop a language where they can work together. They understand the dynamic of cyber if it's an engineer, and if it's a cyber person, they understand the process and the ways people go about controlling or putting safety into the process. I think it's both a challenge for the defense and offense community. You need to achieve that level of integration in your operating teams to be able to expand your mission sets, if you will, or in a defensive perspective, understand what could we not tolerate going wrong, and then how do we prioritize our defense capabilities in order to assure that we can disrupt those paths that matter most, or make good engineering decisions. I would argue that we've failed in the innovation regime, because if we are innovative here, we will change the way engineers actually make engineering decisions. I call it cyber-informed engineering. If you understand the reality of cyber, you might even engineer the process very differently. And a lot of times it comes down to cost. And people are saying, you know what, my God, if we put this wrong product through this valve and we open that valve all the way, we could kill 20,000 people. But we're going to make sure we're going to engineer lots of administrative or engineering controls that will never happen. Well, the controls are digital. They're soft. When the control system is the one that says, hey, I'm going to put in the logic, we can never open this more than 50%. Well, that's nice, but because behind the HMI button, yeah, that valve will never open more than 50%. But quite simply, anyone could then go tell that valve to open up more than 50% by sending the right command to it. And so we don't do our safety basis with any cyber thinking in mind, and that's what's got to change. So that'll be innovation. So I'll end with, from a defense perspective or any other operating environment, focus on your critical paths and choke points to effects. If you start thinking about what could go wrong in the process, it'll help focus you down on areas that an adversary will have to move through. And if you understand that, you can really optimize to be successful. And you can customize the type of tools or capabilities you'll need to observe that. We don't do that. Today we play a total perimeter game. Once we lose the perimeter, and arguably we've had several incidents where we know the perimeter is gone, we've had intrusions into the control system environment, we just now have kind of thrown up our hands like, well, now we're done, which is unacceptable. We're not done. There's a lot of things that we can do. So with that, finally, we have to develop a capability to respond to incidents in an effective manner. Again, that takes engineers and operators working together with cyber folks to formulate an effective response. So folks that just do cyber response, not enough. It's one of the reasons why we do train folks on this ICS 410 class we created. We're very excited about it, but the focus is to take engineers, make them smart facility people. For example, we've had a lot of DOD or U.S. Army facility folks coming to the course, and cyber folks to be able to learn the language to work together, integrate their skills, and understand this important environment that's also kind of challenging. So with that, are there any questions? Yes? So the question is about, if real big incidents occur, there's some thoughts that people would come in with laptops, augmentation teams, and a role for the Department of Defense or the Department of Homeland Security. There's been a debate where the authority would properly sit. Arguably, to formulate an effective response, there's different, think about it as engagement zones. There could be an attack infrastructure, meaning it's an interactive attack. Somebody has gained access, they've pulled exfiltrated data out, they've developed a tailored capability, but they have to interact back in their execution of that capability, right? In that case, the Department of Defense absolutely has a very clear defined mission to disrupt that attack path or to take the fight to the attacker, right? Especially when it comes to critical infrastructure. In the infrastructure itself, arguably, though, I could probably build, if you look at Stuxnet, arguably an unbelievably autonomous, other than the beacon, an autonomous capability that would be delivered in which there was no outer engagement envelope for the defense. And so in those cases, you're talking about trying to formulate a response, a credible response within the environment. Arguably, if we are at war and the War Powers Act, for example, comes into play, I think the Department of Defense will absolutely have a role in defending our critical systems. We haven't been faced with that situation yet, and the legal framework isn't necessarily been applied in that context, but if you look back to World War II, we did deploy U.S. military forces to protect critical national infrastructure from foreign threats. I suspect we would do it again if we had to. In the meantime, in what is probably a Cold War, but a war nonetheless, because people are gaining footholds in these environments today, whether they'd show their capability or not, probably they wouldn't until they needed to. The question is who has the authority. Today we have augmentation teams. If you called voluntarily to ICS CERT, we'd fly out a flyaway team. However, unfortunately, they're limited in the tools and the things they can do. They make recommendations, for example. So it's an area that we do need to work on. The first starting point is probably to develop industry-specific capabilities for investigations. During the August 14th blackout, I was the large utility. I call it the first energy event. I was at AP, a neighboring utility. We definitely were part of it. Blocked out 50 million people. However, when the question was raised strategically is, what if this was a foreign-born adversary? Could that be possible? The answer was, of course it could be possible. Even if a real-world event occurred to initiate it, could somebody put your system at a heightened risk that it would fail? The answer is yes. So the next question was, how do we investigate it? Boy, that was a bad one, right? Because I gave information over, and then I had the Secretary of Energy saying, we can't protect it, and my CEO looked at me like, what did you just do? And I need it back. So the reality is we still haven't worked through some of those issues to develop an investigative capability to even determine if we had an event. So those are significant challenges for us. Other questions? Yes, sir. Yeah. Right. Right. Yes. Yes. Yeah. So the question, comfort level, I'm not going to give you any comfort in my response, but the question is are we, this idea of is there requirements or there's somebody watching this as critical national infrastructure, do they sit in a place where they understand the responsibility? The answer is, in piecemeal, we've done it for parts of the critical infrastructure. For example, the only thing that is regulated today from a cybersecurity perspective are two infrastructures, really. It is the bulk electric system in North America that has a series of CIP standards that they have to meet. And that was based on the concern of attacks against the stability and security of the grid. And then commercial nuclear power plants under NRC has to have a security plan. And those are two infrastructures that have some form of regulation. However, the President laid out in the recent executive order in Section 9, identify for the country infrastructure that could have catastrophic national consequences if compromised. And so that, in theory, is a process to begin to identify areas that says, do we need more? Or is the voluntary framework the best bet to motivate the types of behaviors? The answer will be piecemeal. It'll be in areas where the consequence is tolerable, maybe a voluntary framework is going to work. In other areas, we're going to look at certain processes and say, boy, if that goes wrong, it goes wrong in an unacceptable way. The insurance industry won't even touch this. We're going to have to figure out whether it's regulation law or some assistance package to deal with it. Just knowing is probably a good idea. There's lots of industrial processes based on materials like chemicals or the actual conduct of the process, like establishing vacuums that if you lose the vacuum, you'd have massive explosions. That would surprise a lot of people where they sit and how close the U.S. population is to them and those kind of things. So I think we're going through an educational process to identify and prioritize. But the truth is there are only 2 infrastructures that have any requirements, and they're compliance-based at this stage. So, other questions? Other countries, by the way, are trying to tackle that. France just provided guidance 2 weeks ago as regulation for control systems out to the French companies, saying you can have level 1, level 2, but if you're level 3 control system, that's nationally significant, and therefore you're going to have to certify you've met requirements. So France is taking the move here. Yeah. Addition of smart grid, sure. So smart grid brings 2 major dynamics into play. From a power system perspective, we always had security risks that affect the generation supply, putting power onto a system, and the pathways that we move power over long distances, right? We've never worried about the load from a security perspective because it's very dispersed. So you affect an individual building, big deal, not nationally consequential unless it's like a level 5 containment building for biologics or something, right? So, but smart grid changes that because it means we've now implemented technology, in many cases in a homogeneous technology because we want to manage the technology effectively. And now we have 1 million or 2 million load centers that could behave the same way because we've empowered them to do that. So now an attacker could look at the edge and do 2 things. One, I could swim back upstream in the transmission system because those connections never existed before. Because, hey, going into substation is kind of trivial, to be honest. I mean, I used to have metal thefts like 7 a day. But you'd have to go into the substation, and it's a high-voltage environment. Going onto the side of a house, not a big deal. So swimming up is one threat. The other threat is affecting the meter in the way where you could cause it to all shut off, or worse, shut off, turn on, and do it in a cycle which you can't balance supply, and then you can actually lose the stability of the grid. So smart grid has opened up the edge as an attack surface for the stability of the larger system of systems. That could be problematic, and no one regulates that, all right? So it's regulated by the states from a consumer perspective, so we have a bit of a gap. And so the power system regulation before was generation transmission. You could say, these people, that's their job. Well, in the future, with smart grid deployments, you can't say that. The last element of smart grid is the massive amount of firmware-based devices that leave control of an enterprise or critical infrastructure and go out to the customer and customer sites. No physical protection. It's all firmware-based. There have been lots. In fact, a good friend of Ed and ours, Josh Wright, and Jason Larson developed a worm. There's a proof of concept. They went in there and they grabbed the firmware. They pulled the firmware off, modified it slightly, put it back down, and then a bad meter tells the next meter and it says, hey, you want a firmware upgrade? The other meter says, that sounds great. And then it infects the next meter, and then it starts to propagate. You do that on a wide enough scale, then you have the ability to cause major effects to a large area. So it's opened up a new operating environment for those who want to affect the lights being on in large areas. Super.